Hello everyone, we are Team 6 and we are going to introduce VIREL, which is a variational inference framework for reinforcement learning. Before introducing our framework or the proposed method, I would first introduce you to the background and the related works. The reinforcement learning framework or methodology is a sequential decision-making problem. The agent learns what actions to take to maximize the reward in a given environment, as shown in the corresponding figure. There are various lines of works which actually explore the variational inference in reinforcement learning. The first set of works is the pseudo-likelihood methods. These methods utilize the EM algorithm to derive the pseudo-likelihood inference framework. In particular, they minimize the KL divergence between the target distribution, which is proportional to the exponential return, and the distribution containing the policy to be improved. These methods promote risk-seeking policies, which is actually bad for the performance of the model. As you can see, the classical RL in turn optimizes the reverse form of KL divergence. On the other hand, there is maximum entropy reinforcement learning. The maximum entropy reinforcement learning promotes stochastic policies. More formally, the optimal policy is the highest expectation of long-term reward and long-term entropy. It has various advantages. It has better exploration. It learns alternative ways for accomplishing the task. It also helps for better generalization. For instance, in the presence of obstacles, a stochastic policy can perform much better. However, there are various limitations of this framework. Although it creates stochastic policies, but the deterministic policies are more essential and required. Even though you can create the deterministic policies using an argmax over a stochastic policy, but the argmax is not guaranteed to be the optimal action. To overcome these methods, we replicate VIREL, which is a variational inference framework for reinforcement learning. It provides numerous benefits over these methods and is also the state of the art in this domain. We will then investigate and extend VIREL to multi-agent reinforcement learning. Furthermore, we will improve the proposed method by reformulating the residual error proposed in the main paper. This is the proposed method. The elbow is illustrated here. The proof can be shown in the paper, can be seen in the paper. In particular, the algorithm uses the EM method to optimize this objective. In particular, in the E step, we keep the parameters of arithmetic constant while updating the actor parameters by maximizing the elbow with respect to theta. In the M step, we maximize the elbow with respect to omega while holding the parameters theta k plus 1 constant. Hence, the outer expectation is taken with respect to the posterior found in the E step. These are the advantages over MERL. Even though MERL had the stochastic policy, MERL goes through time. VIREL is only dependent on the current Q function. It doesn't consider the discounted future entropy into account. As you can see from the residual error here, as the error gets lower, the entropy also gets lower. As a result, the policy becomes more and more deterministic. We further illustrate this in this method, in this figure. As you can see at the beginning of training, the residual error is large, and therefore the entropy of the policy is also high, which promotes exploration. As training progresses, the error tends towards zero, and the policy becomes more and more deterministic. A proposed method has various advantages. It naturally learns the optimal policy. The temperature is not a hyperparameter, which is quite important. The function approximator is explicitly used, and the stochastic policies are used for training. The discounting is easily incorporated, and most importantly, it optimizes the reverse form of KL and thus not promoting the risk-seeking policies.
In order to replicate the results of this paper, we plan to use the code which the author has provided on GitHub. And the code uses the Mujo co-simulator, which we have secured a license for. And the experiments are built on an existing reinforcement learning code base. in PyTorch called RLKit. So we downloaded and we tried to run the code already, but we found that the version of RLKit on GitHub has significantly diverged from 2019 when the Virel paper was published. So the authors, we guess, were working on it for maybe a few years before that. So we're going through and trying to find compatible commits for running the given experiments. So we plan to replicate the MuJoCo version 2 experiments on the following tasks, which are Ant version 2, humanoid, and humanoid stand-up tasks. We expect to run into problems, however, as it seems that the current version of the experiments, the current version of the author's code also has bugs which crash the experiment. So that means that the code that they published on GitHub is not the exact same code that was used for these experiments. So we've currently contacted the authors to try to figure out what's happening with that, and yes, we will work through those problems. And we do not plan to replicate the MuJoCo version 1 experiments for the following tasks, which are in the paper, because the latest version of OpenAI Gym that supports these experiments is from early 2017, and they appear to be unsupported by AI Gym currently. So we think that these experiments are just too dated and too old to be useful. And once we replicate these first experiments, we can be sure that our replication is successful. So we think they are not necessary. And then moving on into improvements, we want to extend this Virel framework into multi-agent reinforcement learning, where the problem is that multiple agents have easily learnable dense rewards for specific tasks and difficult sparse rewards for the overall task, which becomes more difficult as the micro agents don't communicate with each other. So our solution would be to utilize Virel to create a multi-agent Virel to take advantage of the superior exploration behavior of Virel while learning. So each micro agent, if it explores the entire state space better, then we think it will lead to a better overall result. So the framework that we intend to apply Virel to in this multi-agent environment is called Multi-Agent Evolutionary RL, and each dense microagent has a set of shared MLP layers and its own classification heads, which are independent. Each agent also maintains its own separate replay buffer. And then while each agent optimizes its own local reward, the whole team is periodically perturbed, and the highest performers globally are selected to form the next generation. So in this way, it's an evolutionary algorithm on the global level. So the environments from that paper provide 4 new environments which we will apply Virel to, which are this predator-prey, physical deception, keep away, and the rover domain. Another thing that we plan on improving or studying about Virel is to do an ablation on the different residual error norms. So in the paper, they define the error norm to have a generic P norm, but as far as we can tell in the code, they use a 2 norm, and we think that different norms may have a different effect with varying dimensionality of state and action spaces. So we want to perform an ablation to see what the effect of different norms will have on the overall performance, and we think it might be a factor that the authors didn't look into that is very important. So here is our schedule. As of right now, we are, I think, a little bit ahead of schedule because we've already started to replicate the results. And yes, we hope to have the replication and improvements done very soon. Thank you.